So we're making progress through this chapter on thermodynamic properties. I'll start with a clicker question. Let's see if we go ahead and start this. I have to give you a little extra time just to read it because it's a long question. What is the difference between subcooled liquid and compressed liquid? Answer A, subcooled liquid has a temperature less than the saturation temperature, while compressed liquid has a temperature greater than the saturation temperature. Or answer B, and then I'll let you read those, okay? So you have right at a minute. What is the difference between subcooled liquid and compressed liquid? All right, getting down to the end here. This is one of those tough questions. What was going through your mind? Were you using a diagram to help you answer that question? Maybe. Maybe one of those diagrams that's a little bit helpful is the PT diagram, and especially out in this region, from this point to that point. What is the 2 points? The triple to the critical point. And if our pressure is greater than along this line, we have the saturation pressure for a given temperature, right? So if I said, okay, here's this temperature right here, you could come up, you get the saturation pressure. If the pressure is above, what do you know? Is it liquid or vapor if the pressure is above that line? It's liquid. And if it's below, vapor. If it's right on it, guess what? It's two-phase liquid-vapor mixture. Or it's in some saturated liquid or saturated vapor or two-phase liquid-vapor mixture state. You can also look this way, thinking about bringing in a pressure. Then you would get a temperature, and you would say, is the temperature greater than that saturation temperature? So along that line, you can think of the pressure as the input, and you got the saturation temperature as a function of pressure. If the temperature is greater, it's vapor. If the temperature is less, liquid. I mean, there's a lot less. We could get to the solid, but I think that's enough to compare. But anyway, so subcooled liquid has a temperature less than the saturation temperature. Is this true? Yes, okay. While the compressed liquid has a temperature greater than the saturation. Can a liquid anything have temperature greater than the saturation temperature? Forget about the qualifier. Can a liquid have temperature greater than the saturation temperature? No, then it would be a vapor. All right, let's take a look. Compressed liquid has the pressure greater than the saturation pressure. So this was the first case, pressure greater than the saturation pressure. Maybe draw it here. That looks okay. While, forget this qualifier, liquid has a pressure less than the saturation pressure. What? Liquid has a pressure less than the saturation pressure? No, that's a vapor. See? So for part A, the first half looks good, the second half looks bad. Part B, or answer B, first part of the question, answer looks okay, and the second part looks bad. And then you just keep going down, because all this is you just moved this section. This liquid has this temperature to right here, right? Isn't that the same? So that's no good. And isn't this the same? That's no good. So which answer is the only valid answer? And why is E the best answer? All those other answers are incorrect. But I tried to emphasize this before, is that sometimes I'll say it's a subcooled liquid. Sometimes I'll say it's a compressed liquid. It's just a liquid that's not close to saturation. Now, as you get a liquid close to being a saturated liquid, it's going to start to want to change phase, right? So these are, what do you call, synonymous? It's just a perspective. You're just looking and saying, oh, is the pressure greater than the saturation pressure? Oh, it's compressed liquid. It's higher pressure than the saturation pressure. Or subcooled. Is the temperature less than the saturation temperature? Oh. And look, maybe go back again from the triple point to the critical point, thinking up here, this is all the liquid. And you can have a perspective from temperature or perspective from pressure, but you're above this line. That's where liquids exist. And then you can think about them being colder than the saturated liquid or higher pressure than the saturated liquid. Okay. Now we have these additional approximations. I already got one email, blah, 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 can't solve this problem. Right here. Right here. This is what I responded to the email questions, like, well, you use the approximation that for subcooled liquids, if you don't have good pressure data, or if it's close to the saturation pressure but slightly above the saturation pressure because it's in liquid state, then you neglect the effective pressure for V, U, and H. And you just say, give me the value of the saturated liquids specific volume, saturated liquids internal energy, saturated liquids enthalpy as a function of temperature only. Okay, that's a great approximation. How will this get abused? Well, it'll get abused a lot of ways, but sometimes they'll go, oh, that must be the same as V sub F, neglecting the effect of pressure and only consider pressure. Wrong. Just check it out. Numerically, it's wrong. Okay, so don't go that way. That's wrong. This is the approximation. It's a function of temperature neglecting the effect of pressure. Ready to solve a problem? I know I need to solve more problems. I'll solve more problems as we get closer to the exam next week, Wednesday, but let's solve this problem. A piston cylinder assembly. So here's an illustration of the piston in a cylinder. Has stops. Those are little protrusions on the side, which means it won't let the piston go any further. The piston can come down and it'll sit right there. That's the furthest that piston can come down. There's stops. Those are the stops. Okay. It has a 0.2 kilogram of water, so we could even put H2O, put the mass of 0.2 kilograms. Initially at 1 megapascal and 500 degrees C. The water undergoes two processes in series, so process 1 to 2 and then 2 to 3. 1 to 2, it's a constant pressure cooling. Constant pressure cooling. So if I don't change the force and I don't change the weight of the piston, but I start to cool it, you can visually think about, or in your mind think about, oh, that piston's going to come at a lower elevation, lower position in that cylinder until the piston rests against the stops, until it moves. So this is kind of like state 1 here, and then there's the location of the piston at state 2. Constant pressure cooling until the piston rests on the stops. The volume occupied by the water is then half of the initial volume occupied by the water. Okay. Then you have process 2 to 3. With the piston resting on the stops, the water is cooled, or continues to be cooled, because it was cooled the first process 1 to 2. Now it's continued from 2 to 3 until the water is 25 degrees C. 25 degrees C. So the first part of the question is sketch the two processes on a PV diagram. Well, to do that accurately, it's not going to be super accurate, but to do it accurately, like, where is state 1? Is it subcooled liquid, two-phase, saturated, superheated vapor? Where is state 1? And we have to place that on the diagram. So in your mind, you're going to say, here's my pressure volume diagram. Here's a dome. If you want, you can make it look symmetric. That's okay. If you want, you can kick out that right-hand side where it's saturated vapor a little, so it's a little bit less steep. That's a little more accurate. Over here where it's saturated liquid, it's very steep compared to over here. Okay. So what's at the top? Critical point. Okay. Now what we do is we say, where is state 1? Then where is state 2? And then where is state 3? So I go and I'll just say, I'm going to organize my information, say everything here is state 1. And then I'm going to talk about the pressure, the temperature, the specific volume, and the internal energy. I know I need at least those properties to answer both part A and then part B. So pressure 1, temperature 1, volume 1, internal energy 1. Do I know any of that information? Do I know the pressure at state 1? And what is its value? 1 megapascal. Maybe I want to use bar. What is that in bar? So what is it in bar? 10 bar, exactly. 10 bar or 1,000 kilopascal is 1 megapascal, true? Okay. Do I know the temperature at state 1? 500 degrees C. Both of those are given in the problem statement. Those look, possibly they could be independent properties. Sometimes pressure and temperature isn't in the two-phase dome, but everything looks like it is, so I would go searching to see if I could get V1 and U1, and I'd determine what is the description of the state 1. And so what do we find? We would go, maybe we would compare the saturation temperature, Tsat, at that 10 bar. If you did, you would find it's around 179.9 degrees C. The saturation temperature at 10 bar at that pressure is 180 degrees C. Our given pressure is 500 degrees C. What do you conclude about the description of the state? What? Superheated vapor. So where would I put it on the PV diagram? Another clicker question. Would I put state 1 in here? Would I put state 1 along that line? State 1 along that line? State 1 in this region? That's this is answer A. This is answer B. This is answer C. This is answer D. Or would I put it out in this region, answer E? So that's a clicker question. Where would I put on the diagram state 1? All right. So what did we conclude? Sometimes I'll even write description, D-E-S-C or something like that. What is the description of this fluid? Oh, it's superheated vapor. True? It's superheated vapor. That's what we just said in words. I didn't write it down. But that's the information you would use to say, aha, it's somewhere out in the region of E. It's somewhere out in the region of E. That's where the superheated. What is B? Saturated vapor. What is A? Two-phase liquid vapor. What is C? Saturated liquid. What is D? Compressed liquid or subcooled liquid? Your choice on the terms. All right, so there we go, right? Okay, now this is a little cluttered. And if you have your tables with you, can you get the other two values now for state 1? What is V1? 0.3541 meters cubed per kilogram. And U1? 31.4. Yeah, that's a 0.4 kilojoules per kilogram. So 3,124.4 kilojoules per kilogram. Okay, so there is state 1 somewhere out there. Should I put state 1 above this pressure right here? I forgot the name of that pressure. Pressure critical point for water. 22 bar. 22 bar, isn't it? 220 megapascal. Tell me the critical point pressure. 220 bar. 200, did I say 22 bar or 220? It's 220 bar. Yeah. So here's 220. We know that this pressure is 10 bar, so it's well below the critical point. It's below that pressure. Okay. So it's somewhere like that. Now, let's make a list for properties at state 2. The pressure at 2, do I know that? 10 bar. It's a constant pressure process. Cooling. Okay. How about the temperature 2? Not really. V2 and U2. So we know this pressure, that's one property. What I don't really know T2, it's been cooled. But we know that it hit the stops. So which of these properties, clicker question, do I have the best chance of getting to know given the information? A, temperature at 2, B, specific volume at 2, C, internal energy at 2. I'll take your responses right now. And I may have mentioned it last time about rereading the problem statement. I have to read it often, and sometimes you go back and you glean, and now you say, water occupies a volume, 1/2 of its initial volume at the final state 2 of that process. Isn't that the key words that you used? If that's true, so then what is the relationship between V2 and V1, the initial volume? Isn't it 1/2 V1? How about the specific volume at state 2 compared to the specific volume at state 1? The mass didn't change. It's held constant. It's a closed system. So the specific volume at state 2 is 1/2 the specific volume at state 1 from the given information. So that's our second property that we can determine with a little bit of work, just by reading the problem statement, that this V2 is now 1/2 of 0.3541, which is change color there, 0.1771 meters cubed per kilogram. Now, armed with that information, can I determine the temperature at 2 and the internal energy at state 2? Can I find the, description of the state? Where is state 2? Is it superheated vapor? Is it saturated vapor? Two-phase liquid vapor? Saturated liquid? Subcooled liquid? Where is state 2? So you guys need to bring your tables or something to get the most out of these, because we're in chapter 3. Chapter 3 is all about evaluating thermodynamic properties, and the only way you're going to get good at it is not by watching but by doing. So if you can bring your tables for the next couple lectures, that would be helpful. So what do we find? Right, so what you do is you go to table A3, which is the saturated water table with the pressure as the easiest input. And you look at 10 bar, and you want to find where V2 is. Is V2 greater than V sub G? Oh, superheated vapor. It's because right here you're going to be cooling it. But do you stop right there? Is that state 2? Or when you cool it, does it go inside the dome? Is that state 2? Or does it go all the way through the dome and outside the dome over there? Or does it go this way? Well, we know that it's not going this way, is it? Because look, it went to half of its original value. So if it started here at 0.3541, it ends somewhere over here, 0.1771. So, but where is 0.1771? You compare it to V sub G at that pressure of 10 bar. That V sub G at the pressure of 10 bar is 0.1944. Is that correct? And now what do you deduce? This value right here is 0.1944. You started at 0.3541 and you're ending at 0.771. Okay, and then V sub F is a very small number. V sub F is 0.00112 Can you help me? I can't read it. 273. So V2 is between V sub F and V sub G. So we conclude the description. It's two-phase liquid vapor. Liquid vapor, come on now, right, vapor. Liquid vapor mixture, right? We probably want to get the quality of that two-phase liquid vapor mixture. Once you have the quality, then you can get the internal energy. Oh, by observation, what is the temperature at state 2? Anywhere between here and here, if state 2 is in there, what's the temperature? 179.9. It's the saturation temperature at that pressure of 10 bar. So anyway, this is where state 2 is, somewhere there. So the process goes just like that. That's the process, 1 to 2 on the diagram. I'm getting a little ahead of myself. I know that for part B, I want to calculate the work and the heat transfer. So let's get the properties at state 2. You get the quality by B minus V sub F divided by V sub G minus V sub F. And when we calculate the quality at state 2, let me see if I can read that number off, we find that it's 0.9102, about 91%. So I should have stopped 2 a little closer to saturated vapor, okay? I should have stopped state 2 closer to saturated vapor. Maybe, should I clean it up a little bit? Put state 2 kind of closer here. That's still too far away, but there you go. Now, once I know the quality at 2, I can get the internal energy at 2. What's the equation? I want to write it down here. U sub F plus the quality at state 2 times U sub G minus U sub F. Are these equations becoming your good old friends? Won't need to look on the equation sheet for one like that, will you? Maybe the first time or two, but after a while, no, you won't. And so this becomes 2420.05 kilojoules per kilogram. Okay. Let's get state 3 now. It says it's cooled until the water's at 25. So let's put P3, T3, V3, and U3. And what about the pressure at 3? Do I know that? How about the temperature at 3? Well, it goes to 25 degrees C. What about V3 or U3? Which other property can I determine? Clicker question here. Is it A, B, or C? What is that other property which is most readily determinable from the problem? Is it the pressure at 3, this volume at 3, or the internal energy at 3? Well, I'm sure that you're having to do what I've already mentioned, reread the problem statement, right? What's happening between state 2 and state 3? Well, the piston is resting on the stops, and it's being cooled. Heat transfers out of the system, right? So where's the piston at state 3? Right there, same place. Okay, if the piston didn't go anywhere, did the volume change? Is the volume at state 3 equal to the volume at state 2? Yeah, it is. And so, guess what the best answer is? Don't we know V sub 3? What is the value of V sub 3? The value of V sub 3 is 0.1771 meter cubed per kilogram. And now those two properties help us fix the state and now march around and get the other properties, true? Okay, so now that we know it's here, I need to figure out if the quality is, so I look at, I find that V sub 3 is between V sub F and V sub G, but those V sub F and V sub G's are evaluated not at 190 79.9 degrees C is the saturation temperature, but 25 degrees C is the saturation temperature. So I go and I check, and I flip to table A2, 25 degrees C for the saturation temperature, and I find that that value of V sub F is 0.00100. Help me a little bit. How many zeros are there? And then a 29. And V sub G is 40.36. All right? So I see, look at V3 is between the V sub F and V sub G at that lower temperature of 25 degrees C. Hence, I get the quality at 3. And to calculate the quality at 3, just like you calculated the quality at 2, you find that now it's 0.0041. What? It's really close to being all of the mass is being condensed. There's just a little bit of that mass left that's still in the vapor phase. To draw this accurately on a cartoon, right, I need to really draw this up and kick this way out and put state 2. It's even going to be worse than that. It's hard to draw it to scale on here because when it cools down, it stays constant volume to state 3, doesn't it? But this edge goes so far out like that that it's now low quality steam at state 3. Oh, I forgot to emphasize, what is the pressure? What is the pressure at state 3? Isn't that the saturation pressure, which is 0.0316 something bar, 67 bar, which is 3.17 kilopascal? True? Mm-hmm. Saturation pressure at 25 degrees C out of table A2. 6969. 3.169? 3169. Right? Like that? Did I fix it? Thank you. And now, knowing the quality, I get the internal energy, U, because I'm going to need that for the next problem. And internal energy is 114.24 kilojoules per kilogram. All right, so here is the answer for part A. It's a PV diagram. You put the dome on it. You show 1 is superheated vapor, 2 is two-phase, 3 is two-phase at a lower pressure. Here's another clicker question for you. At state 3, at state 3, somehow there develops a hole in the side of the piston cylinder apparatus. A hole now, somehow there's a hole in the side. And I have what's on the inside? Water. I'll just call it steam. Okay. What's on the outside? Air. True? Now, the question I have for you, will the air rush in? That's answer A. Or will the steam rush out? That's answer B of the hole. You have two options. Which way, once the hole is developed, whoop, there's a hole now. Which way is the fluid going to flow? Air rush in, answer A. Steam rush out, answer B. This is at state 3. At state 3. Yeah, this air is at 1 atmosphere pressure outside. Let's say it was in this room. Does everybody have enough time? All right. So, how do you determine which way fluid flows through a little hole? By temperature difference? Internal energy difference? Pressure difference. Okay, we got to know something about fluid flow, right? Does fluid flow from high to low pressure or from low to high pressure? Which way does the fluid flow? High to low. So basically this boils down to where's the pressure higher? On the air outside in this room, what's the air pressure? Give it to me in ATMs, 1 ATM. Give it to me in kilopascal, 101.3 kilopascal roughly. I know I'm approximating standard atmospheric pressure. Give it to me in bar, 1, right, 1.013. So outside we have a pressure of 1 bar, and then at state 3, that's what the question was, how many bar on the inside? 0.03. Okay, let's try and make a comparison. 100 pennies, like $1, or 3 pennies on the inside. Which is greater? It's 1 bar on the outside and 0.03 bar on the inside. Which is a greater pressure? So this is always interesting. It's like, yes, in some systems you can have steam, pure water on the inside, a hole develops, steam doesn't leak out, air leaks in. And it does happen. Because we will condense in a power plant steam, and the condenser will have the pressure on the inside of the tubes lower than atmospheric pressure. All right, so let's go ahead and grade this one. Look at that. So isn't A the right answer? The air will rush inside if a hole develops? All right, hopefully next time I ask a question like that, we'll be closer to 100% correct, right? All right. Now they ask questions. Calculate the work and the heat transfer for each process in kilojoules. I have to scroll down. I'm sorry, I hate to do that, but I have to. So for the work, cap W, because why do we want it in cap W? It's in kilojoules. That's going to be the integral PdV, constant pressure process from 1 to 2. So we find the pressure times the mass times the final specific volume minus the initial specific volume. Done those a few times. What is the pressure? Put in 1,000 kilopascal, because that's my favorite pressure when I'm multiplying by meters cubed per kilogram on the specific volume. I have 0.2 kilograms, and then we have 0.1771 minus 0.3541 meters cubed per kilogram, and the units will work out, and we get the work 1 to 2 is equal to a negative 35.4 kilojoules. Make sense? Now the heat transfer, the Q, we do a first law analysis. So we say, okay, Q 1 to 2 in minus the work 1 to 2 out is equal to U2 minus U1, neglecting changes in kinetic potential energy. True? So Q 1 to 2 is going to be, let me kind of write it up. I'm running out of room. Is the work 1 to 2 plus the mass times the lowercase u2 minus u1. And we have all of those u1, u2 values. And let me just say that Q 1 to 2 is a negative 176.3 kilojoules. It's cooling. It's not positive heat added. It's negative heat removed. It's coming out of the system. True, it's a cooling. Now we go and say, what is the work 2 to 3? This is on the PV diagram, the process 2 to 3. I'm going to ask a clicker question, help you recover some points here, right? Is that going to be greater than 0? Answer A. Equal to 0? Answer B. Less than 0? Answer C. What is that work 2 to 3? Can you determine if it's going to be positive? Answer A. Equal to 0? Answer B. Or negative? Answer C. Should have asked that for the work 1 to 2, shouldn't I? Oh well. Missed many opportunities for clicker questions, right? Everybody in, hopefully? All right. Well, on a PV diagram, when the line is straight up and down, what's the area under the curve? 0. We didn't do any changing of volume from 2 to 3. Hence, the correct answer is B. The work is 0. There's not a whole lot of, I just have to make that observation, and then if I want to put units on it, I can put units on it. But that's the answer for part B. There's 4 parts to part B. That's one of the parts, the work 2 to 3. Now, how about the heat transfer? Well, Q 2 to 3 is going to be the work 2 to 3 plus the mass times U3 minus U2 from the first law. And we got those specific internal energies. We know this is 0. And so we calculate Q2 to 3 is negative 461 kilojoules. I encourage you to resolve this problem. That I mentioned how to solve problems in thermo. Use the technique of taking the paper that you solved it on, ripping it up, crumpling it up, throwing it away, get a blank piece of paper out, and resolve the problem again. Striving to be neat, striving to not go down dead ends like we normally do. I do a lot of dead ends when I'm solving a brand new problem, like, oh, I did a lot of work, but it's not helpful. I got to back up and continue on the path here. And get better at solving it. Okay? Ideal gas equation. So, how many people remember the ideal gas equation that PV is equal to NR bar T? We talked about that last time, each of these terms. What does this P have to be in? Absolute pressure. What about this T? Absolute temperature, needed in Kelvin for SI units. What is this R bar? The universal gas constant. So it has a value, R bar is something like 8.314 kilojoules per kilomole Kelvin. You know what? Sometimes it's really convenient when you're dealing with pressures and volumes to substitute for that kilojoule and write it as 8.314 kilopascal times a meter cubed divided by kilomole Kelvin. What? Is a kilojoule equal to a kilopascal times a meter cubed? It is. And a lot of times that's a very convenient form for R bar. True? Okay. If I take and I multiply by molar mass here and divide by molar mass here, did I change the equation? No, it's the same equation. I'm good with my math. I didn't mess it up. It's still a good equation. And then I recall, oh, the number of moles times the molar mass, that's equal to the mass. So I can either talk about the amount in kilomoles or the mass in kilograms. What is big M again? The molar mass. How many kilograms per kilomole? So you can rewrite this equation, PV is equal to MRT. What happened to the bar? Well, R is equal to R bar divided by the molar mass. Of what? Of the gas of interest. So we wouldn't call R the universal gas constant. We would just call R the gas constant of interest. If it's air, we use the molar mass 28.97. If it's something like hydrogen, you look up its molar mass, it's around 2. And you would get a different R. The universal gas constant, as long as it's an ideal gas, R bar is the same value, but R changes depending on the gas. This is always tricky for students. Difference between R and R bar. R is equal to R bar divided by molar mass. True or false? True. Here is a table in the textbook. They could have put it in appendices. I wish they would have, but they didn't. And what do they have right here for a column? This is the R for air, for ammonia. You don't have to memorize these. you just have to look up the molar mass of each of these components and then compute R when you need it by R bar divided by the molar mass. But every now and then it's helpful to just remember, oh, for air it's 0.287 look at the units, kilojoules per kilogram, not kilomole Kelvin. Okay? If you wanted to work in the BTUs and pounds, yes, we have R bar in BTUs, pound mole, and degree R, as well as you can put the gas constant in United States customary system of units. We jump back here. This is not the only form. We can then do this. What's P V equal to RT? Where what is V? Isn't that the volume per unit mass? And then another form, which is not as useful in this class, but definitely in fluids, P is equal to rho RT. What? Well, is rho equal to 1 over V? And so this is used a lot in ME3663, fluid mechanics. But it's a simple ideal gas equation. All right, another one to do is just stay with PV is equal to nRT and put it over here like PV divided by N is equal to R bar T, which is PV bar equal to R bar T. What is V bar? That's the volume per amount, not the volume per mass, but volume per amount. So what are the units on V bar? Something like meters cubed per kilomole. So we use it a molar description of the ideal gas equation, a mass description ideal gas equation. There's multiple versions of the same equation. Get familiar with them. Did I miss any of you? Do you have a favorite one that you don't see up here right now? But you want to get familiar with them. Well, there's a couple things about the ideal gas equation. One is Joule did an experiment. Is this the same guy we talked about before? He did a paddle wheel experiment, the work and equivalence of heat. Yeah. Well, he did another experiment about 1845, and it's not that complicated. He basically took a chamber and another chamber. One he filled with an ideal gas, maybe inside A, and the side B he evacuated. He put a vacuum pump and he evacuated, got everything out of it. Okay, it's a little hard to do that in 1845, but he was able to do it. And he had a little valve here, and he put it in a water tank, and the water tank's well insulated. There's no heat or work. It's an isolated system. The water and the air containers are all isolated. He has a nice, accurate thermometer, so he could tell if the water temperature changes. And he deduces after this experiment, I'm going to explain in a second, that the temperature of the water never changes. If the temperature of the water never changed and there's no heat transfer between the water and the surroundings, what can you conclude between the air that's ideal gas in tank A during some process? Was there ever any heat transfer between air and the water if the water temperature never changed? There's no Q. So what he found was, by measuring the temperature of the water, that there was no heat transfer between the water and the air. The water stayed constant temperature, the air stayed constant temperature, or the ideal gas stayed constant temperature. Because he mixed it up. He would try air, he would try nitrogen and argon and helium and whatever gases he had. A lot of tests he did. But with this valve right here, the process that he did, start it, get everything in equilibrium, look at the thermometer. Then he would open the valve, look at the thermometer. Any change? No change. No change. And what he's able to do is he deduced it by looking at the first law for that ideal gas. He said that write it out like this. Q for the ideal gas minus the work equal to the change in the internal energy. I'm going to put it like this. The mass times U final minus U initial. Okay, what was the initial? The initial, first of all, there's no work for the ideal gas. It expands into a vacuum. It's not pushing against anything. I know it expands in the process, but it pushes against the vacuum. Why is Q 0? He didn't determine, he observed no temperature change of the water. Hence, there was no Q from the gas to the water or from the water to the gas. So he deduced that U2 is equal to U1 for the ideal gas. Internal energy didn't have to change. But what changed? At state 1, it's a function of the temperature 1 and maybe the volume of 1, or the internal energy at state 1 is of temperature 1 and pressure 1. But the volume of the ideal gas changed, didn't it? The final volume is greater than the initial volume because it expanded into the evacuated side. And what about the pressure final? It was less because it expanded into the evacuated side. So what he concluded, I know I'm going this a little fast here, is that for the internal energy of an ideal gas, it's only a function of temperature. It is not, the internal energy is not a function of pressure for an ideal gas or a function of volume. For a real gas, like steam, close to saturation states, then it is. But for an ideal gas, the things he tested, it's not. So when we talk about ideal gases, there's three things that make up the model. The equation, makes sense? That observation from Joule's experiment, that internal energy of an ideal gas is only a function of temperature, and the specific enthalpy is only a function of temperature because what is the definition of H? H is equal to U plus PV, but guess what PV is? RT. And so if this is a function of temperature only, R is a constant. That's a function of temperature only. It's the simplest temperature only. Temperature, it's just temperature. And so hence, H is a function of temperature only as well. So three things when you talk about an ideal gas model. The equation, U is a function of temperature only, and H is a function of temperature only. Thank you for your time. We're out of time. See you next time.